Okay, so my name is Mathieu Romer, and I'm going to speak to you about interprocedural shape analysis using separation. No?
Check if it's
Okay,
muted or not.
sorry.
Let's see. I think that will be better.
Okay, yes, I can hear myself. So what is this talk about? We want to distinguish two kinds of analysis. The first is state analysis, and what is the goal of a state analysis is to compute a set of reachable states. And with this, you can answer to state properties, like is this pointer, does it have null pointer dereference, or does this program preserve some structural invariant on data structures? On the other hand, you have other analysis that we call transformation analysis or relational analysis. And what it does is that they compute abstract transformations. And an abstract transformation is a relation between the input and the output of a program. And with this, you can answer to other questions like, does this program modify the linked list received as an argument? Or is this sorting algorithm in place? Or does it allocate memory, etc.? So what is this work about? Is about abstract transformation, and specifically we show how we can use this abstract transformation to summarize procedures and to avoid redoing the analysis for a procedure several times. And in particular, we want to apply this to the context of shape analysis using separation logic. Just a quick overview of what our technique is about. Here you have two functions, two C functions. One is called append. It takes two linked lists as an argument, and what it does is that it will append the second list at the end of the first linked list. And the double append, it calls append twice, and it takes three linked lists as an argument. It will concatenate everything. So how can we analyze double append? The first idea is to perform a state analysis, and when we encounter a call to append, we just pretend that we inline the call. Then we reanalyze the function, and when we come to append again, we will reanalyze append a second time. So one of the benefits of this is that it allows a very precise analysis of the procedure, but the drawback, of course, is that the analysis is repeated for each calling context, which can be quite slow. Also, it is not able to handle recursive procedures. So the idea is that if you have some abstract transformation that represents the behavior of the append function, when you want to perform the state analysis, you will somehow be able to apply this abstract transformation to the states that you have, and using that, you can compute what the double append function does without having to reanalyze the append function, which is more efficient. But what we also want to do is to have an abstract transformation for the double append function. So we want to perform a transformation analysis on the double append function. So now how we do that is that we start from an initial state in double append, which describes the initial state of the memory and says that it has not yet changed. And we will use an operator that we call abstract composition, which is an overall approximation of a composition of relation. And by applying this abstract composition, we will be able to have a summary of what the double append function does. And this also implies that we perform the state analysis of the double append function. So in the case of shape analysis, this is how it will look. So our summary for append looks like this. We have two linked lists, and the idea here means that the linked list will not be modified except for the end of the first linked list, which was initially a cell containing 0, in which no points to the end of the second linked list. And when we will apply the composition in the double append function, we start from an initial state which states that we have three separate linked lists, and by composition, we will be able to derive the fact that at the end of this function, we have modified this linked list so that they are all concatenated. This is a perfect representation of what double append does. So in this talk, there are two main contributions, which is first the interprocedural analysis by this composition of abstract transformation, and second the application to the shape analysis. And I really want to focus today on the interprocedural analysis part because I really think that it can be of use even outside of the shape analysis world. In any case, when you might want interprocedural analysis. So for this, I will use a simpler abstraction than the shape analysis abstraction, and I will use a standard state analysis abstraction, which is the linear equalities over program variables. So this is a standard polyhedric model of a domain of Kuzo and Albrecht. So in this domain, the analysis of a function which assigns z to x plus 1 with an initial state being x smaller than y is this output state. And the corresponding abstract transformation corresponding to this state abstraction is this. It is a linear equalities over prime and unprimed program variables, where the prime program variables, they represent the next version of the variable. So for instance, if I take the same program and I apply it to the same input state, then I will get in the end that we still have that x is smaller than y, and in the end, z prime, the next version of z, is equal to the previous version of x plus 1. Okay, so let's dig down on what this abstract transformation really means. So I take the same abstract transformations that I showed you, and what must be understood that there are three different components hidden inside this abstract transformation. The first is that it includes a description of the input state. From these relations, you can derive that initially you had x smaller than y. So it contains the input state. But it also contains output states. So basically, the output state is the relation that you have between the prime variables. So you can derive that x is smaller than y because x prime is equal to x, y prime is equal to y, thus x prime is smaller than y prime, and thus in the output state you can say that x is smaller than y, and similarly you know that z is equal to x plus 1 in the output state. So it contains both the input and the output state, and it also contains a description of the relation between the input and the output. So x has not changed, y has not changed, and z prime is equal to x plus 1. So yeah, what must be understood here is that you both encompass the pre and post condition represented at a pair of abstract states, and you are more precise than that. Now, the main operation that we want to perform on abstract transformations is the composition of relations, and the abstract composition of relations. So this is an abstraction of the composition of relation. What the composition of relation does is basically, if you have a relation which explains how you can go from the white states here to the colored states here, and you have another transformation which explains how you can go from the colored states to the black states, you will try to find out if there is a path that goes from the white state to the black state. And so you will find there is some notion of intersection going on here, trying to find what are the common states between here and here. And in the end, you will find all the paths that go from white to black. And if you want to do that in the abstract, basically, we only do an over approximation. So we replace the equality here by inclusion. So this abstract composition operator is really the intended meaning of what it is to use a procedure summary. So for instance, here I have three different functions. The f function only increments x and can be represented by this procedure summary where y and z doesn't change, x prime is x plus 1. Here g only assigns x to y. And here you have the composition, you have first a call to f and a call to g. And the meaning of h is really the abstract composition of the two relation abstract transformation tf and tg. And so yeah, abstract composition is really the operator to use an abstract transformation. Okay, so until now, what I've presented was what I call global transformation summaries. These are abstract transformation which represent all the possible behavior of function f. Meaning that for any input state, you will have to represent the corresponding output state in the abstract transformation. So what's really nice about this is that it allows a purely bottom-up interprocedural analysis in the way of what Chanier and Nueli call a functional approach to interprocedural analysis. But there is some issues, it's that it leads to some imprecision in the abstract transformations. So for instance, here I have a function f which does a nonlinear assignment to the z variable. And because it's a nonlinear assignment, it cannot be represented using a polyhedral abstraction. And so in the end, we don't know anything about what the z variable contains. It's a bit of a shame because if f is applied in the context of a g function where x is a constant, actually this assignment is a linear assignment because x is equal to 3. So we could be able to represent exactly what z does in this function. So there is a loss of precision here. So our solution to this problem is to use what we call a context transformation summary. So it's a pair of an input of an abstract state and a transformation and an abstract transformation, which represents all the behavior of the function f, but only for some precondition of f, and the precondition is given as an abstract state. So what does it mean formally? Is that for any state in the precondition described by SF, the pair of the corresponding output state must be represented in the abstract transformation. So now we can redo our analysis. Basically, what we will do now is that we will compute the summary for f, but only in the case where x is equal to 3. And in this case, we are able to perform a transformation analysis of and to have a summary of f which is precise, which is exact actually. When we use this summary, we are allowed to use this summary because well, it corresponds to this state, and we are able to have a completely precise representation of what G does. But on the other hand, previously we could be using a completely bottom-up analysis, and it will no longer be the case because we have to know for which context we want to compute the summary of the functions. So this suggests that we will be using a top-down algorithm. The idea is that when we will try to call some function, we will see if we can use this summary. If that's the case, that's nice, we reuse the summary. Otherwise, we try to recompute the summary with a larger calling context, and we do that until we iterate. So an interesting question that and a mistake that we made initially is that why do we need both a context and a transformation? Because earlier I told you that the abstract transformation they contain the input state of the transformation. And in all the examples that I gave you until that, where you have simple functions for f, we have actually that the context corresponds to the input state of the abstract transformation, so it seems to be quite redundant. But there are also many cases where it's not the case. So consider, for example, this function. So if x is bigger than y, we have a while and infinite loop that will never reach the end of the function. If x is smaller than y, then we have a runtime error and we will also not reach the end of the function. So we will only reach the end of the function in the case where x is equal to y. And this is reflected in the abstract transformation where we have this condition x equal to y here. So basically what this means is that our abstract transformation is able to infer some kind of precondition of of what is necessary for the function to return. And in that sense, it's a bit similar to the abduction algorithm of infer, for instance. So we need to have both. The abstract state describes the context where the summary can be applied, and the I of TF it describes the precondition for the states to return. But you can also apply the summary even if the function does not return. Okay, so this is the main idea of our algorithm. Basically, it's a top-down and hybrid between inter and intra-procedural algorithm. So the idea is that for simple statements, we will use normal relational abstract transformers, which are as precise as we can get. And we will use abstract composition only in the case of function calls. So when we have a function call, we want to determine if the current context transformation, if the summary can be used. So basically, we look at the output state and we do a comparison in the state domain with the context. If it's good, we can reuse the summary. Otherwise, we need to recompute it. And we recompute it with a new input state, which is the join between the previous one and the new one. And once we have done that, we can use the abstract composition to perform this, to use the summary of F. And this algorithm can be extended to NL recursion. Basically, the idea is to grow these context transformation summaries until we reach a fixed point. Okay, now while we want to extend this towards this relational separation logic, there are two main ideas here. First, with what I presented, there will be a lot of spurious recomputation of summaries. It will work, but it will be slow. And the idea is this one. Imagine that we have this function g with two calls to f. And in one case, we have y equals 3. In the other one, we have y equals 4. We are here. And so in the first call to f, we have computed a summary in the case where y equals 3. But when y equals 4, we cannot reuse this summary because the context doesn't apply. And it's a bit of a shame because the behavior of s does not depend at all of what is the contents of y. So the idea to solve this problem is to use the local reasoning, the frame. For this, we will use the frame rule of a separation logic. Actually, it will be the relational frame rule of the relational separation logic. So how does this work? Now the summary of f doesn't speak only about x and does not speak at all about y and z. And the context for SF is more general, so that in the second case, we can use the summary for F. But what we will have to do is to complete this summary with another abstract transformation that says that the part of the memory that is independent of F is not modified. So we will use this transformation and we will use this with the fact that y prime equals y and z prime equals z. So with this, we are able to use summaries more often. And the other thing that we want to use is to allow unbounded memory, because for now we have only a simple representation of what is a memory. What is the idea is that we will gradually change the representation that I've given you to a more complex one. And the first step for this is that we will separate the description of the memory and the description of the numerical representation. So we will have a separate numerical domain, which is a set of variables with constraints between these variables. So we have alpha, which corresponds to the ones that are here. And we have a memory description, which says what are the values of each of the variables in memory. So this is the first step. And basically, those are completely equivalent. Then we will introduce a predicate which we call ID, and the idea is to say that we can say that two memory regions are equal without having to express manually that each of the value is equal. This will be important when we use unbounded region of memory because we cannot enumerate all the values that are in memory. And finally, we will generalize to arbitrary representation of heaps, like the one that I presented earlier, for instance, using linked lists, etc. Okay, let's move on to the evaluation. So basically, we implemented 3 analyzers in a plugin of Pharmacy with 3 modes: a fully inlining state analysis or shapes, fully inlining relational analysis, and relational analysis is based on summaries. And our main case studies was to analyze a part of Emacs. So why Emacs? Because it's a large C program which does heavy manipulation of linked lists and complex data structures. And basically, what should be remembered here is that the relational analysis is slower than the state analysis because it contains all the results of the state analysis, but also computes additional properties. But on the other hand, we can use the relational analysis to to use as a procedure summaries. And thanks to that, we can be much faster than the original state analysis. So in the end, we will be the summarized analysis will be faster than the state analysis, which was quite expected. And we found out that often we don't have to recompute functions a lot of times. We find quite easily the most general context in which the functions will be called. And because composition can introduce some loss of precision, we wanted to verify that if it was the case, and no, our compositional analysis was exactly as precise as the state and relational analysis. And of course, we can infer relational properties, like properties over modification of some functions, which are stronger than state properties. So, to conclude, some key takeaways is that these contextual procedure summaries, you can represent them using this abstract transformation. They are very useful for that, but it's also very useful to complement this abstract transformation with an abstract state which describes the context in which you can apply the abstract transformation, and it allows much more precise analysis of interprocedural analysis. Then you can use this summary-based transformation analysis by using this composition abstract composition operator. And of course, you can apply this to shape analysis using separation logic, but it's really important to see that you can apply this in many other contexts also. And in the end, these transformation analyses are not as well known as state analysis, but they are very useful because they capture very natural abstraction for the programmers. It's very common for programmers to ask themselves what part of the function is modified by, what part of memory is modified by a function, for instance, and so they can verify very useful functional properties. So thanks for your attention.
Matthew, do you have any questions?
Hi, thanks for the great talk. I'm not super familiar with shape analysis, so of course this question might not make sense logically, but I'm curious about the choice of separation logic. Could I plug like a 3-value logic in there as well, or like other shape analysis techniques, or do you think this approach really needs some feature of separation logic?
Yeah, so I think the beginning of the talk was really completely independent of separation logic, where separation logic makes sense. And shape analysis makes sense is where you want to use embodied memory, of course, and you have to do some kind of shape analysis. But also this frame rule, I think, is very useful. So probably you can have some variant of this frame rule in other settings, but I'm not sure you can really do something like this in TVLab. Probably something can be done. What I can show you is that this notion of relational separation logic is basically something which is above what is separation logic, but it's actually above any memory abstraction. So you can use any memory abstraction and apply this relational separation logic. So it's quite independent of the underlying memory abstraction, which could be something else, for instance, type-based abstraction.
Cool, thank you.
Any other questions? Hi, this is very interesting. How do you decide what's the right context for these contextual to not use in position?
Yeah, that's a very interesting question. So what we do is basically the first time we analyze a function, we use that as a context. But because it's too general, we want to use this frame rule to make it more, well, less specific. So basically, how we do this is we see what are the parts of the memories which are reachable from the function, and we decide that this is what is important for the function, and the rest is the part which is irrelevant to the function. And then we do it several times until the summary is big enough.
Okay, so it's more or less an automatic process. It's not something that you have to do.
No, it's completely automatic. The only drawback is that you may have to recompute the summary several times during the analysis. But for instance, if you launch several analyses, then you can reuse the result of the first analysis immediately. So it's not very a big deal because, as we saw in our analysis, at most some functions were analyzed 3 times. So you had to recompute the summary 3 times to get to the end. And if this function calls subfunctions, often these subfunctions, well, the reanalysis takes less time because it uses some functions which are already analyzed and so on. So in the end, it's not that expensive, it's the computation.
Thank you. Can I ask a question? So the techniques that you use here for summaries, do you think those can be generally used for any form of data analysis?
Yeah, I really think so because that's why in this talk I wanted to show that it could be applied completely independently of shape analysis with this prime and non-prime variable. So you still will need to change your state analysis into a relational analysis. Often this technique of prime variables can be done in many other cases. For instance, there are TVLA versions which does this prime and non-prime thing. So in the kind of finite memory abstraction, it's quite easy to do. In other cases, yeah, it's more complicated.
Thank you.
Another question?
Yeah.
Thank you for the talk. So I'm curious how does your analysis convert to infer? So you already mentioned that inferring the precondition is similar to abstraction. I'm curious more maybe at the high level, since infer is also an abstract interpretation engine at the end of the day, where they manage to plug in lots of different domains and then from there it's also multiple different analysis. So I have the feeling the goal is similar with your work.
I'm not sure the goal are very similar because what we really want to do is to, in the end, have a completely sound verification. I think the inferring was more to be a fast verification that could be applied at scale. And in particular, I think what infer does, they also restrict the analysis of their function to so specific context, but I think try to do more very bottom-up analysis, and if their context is not large enough, well, they don't care because their goal is more to do bug finding than to do real proof of the system. So I think this will be one of the main differences between our algorithm and what infer does.
So your aim is to maintain science.
Yeah.
Thank you.
Another question?
So, thank you very much for the talk. It was really clear. So one of the things you say is that the most analyzed function is analyzed 3 times. And that is very confused, but it can also be quite surprising to see that it converges so fast. Was it what you were expecting, or were you surprised as well when you saw the speed of convergence?
So I think if you have a precise numerical analysis, this will not be the case because often you can have several steps in your analysis, but in a shape analysis, often like if you have a linked list, you have like three cases, which is a empty linked list or a full linked list. And as soon as you join one element linked list with an empty linked list, you have a full linked list. So because 8 of the infinite lattice is small, I was expecting that we would converge quite quickly. So I think it should depend on the 8 of your lattice. But this will need experimental validation.
Okay, thank you very much.
Yeah, let's thank you again.
Thank you.